Hello, so today I'm looking at M3 International A-Level May 2005. This is question 2, and here we have a spacecraft of mass m moves in a straight line towards the centre of the Earth. The Earth is modelled as a sphere of radius r, and S, the spacecraft, is modelled as a particle. When S is at a distance x from the centre of the Earth, the force exerted by the Earth on the spacecraft is directed towards the centre of the Earth. The force has this magnitude where k is a constant, so k over x squared, and show that k is mg r squared. So in this case I have the Earth, I know the radius is r, and I know the distance from this particle is x, which is measured in this direction. I know that when you have the particle here, we've got this force of k over x squared in this direction, and another thing that I know is the size of this force when it's actually on the surface of the Earth. So on the surface of the Earth, we know that x equals r, and we know that the force is mg, where m is the mass of the spacecraft. So I know that in that case I have mg equals this force with an r in the place of the x. So then I get that k is mg r squared as required. So that's the first two marks. Then it says, when S, the spacecraft, is at a distance of 3r from the centre of the Earth, the speed of the spacecraft is capital V. Assuming that air resistance can be ignored, find in terms of gr and v the speed of the spacecraft as it hits the surface of the Earth. So I know that I can do Newton's second law here, because if I look at what's happening, I've got my spacecraft, which has this force of k over x squared towards the Earth, the centre of the Earth, and I know if x is measured from the centre of the Earth out in this direction, then the acceleration is in this direction. So I know that from Newton's second law, the forces this way minus the forces that way equals the mass times the acceleration. So I have 0 minus k, which I know is mg r squared over x squared, equals the mass, which is m times the acceleration. Now for the acceleration, I can either use dv by dt or v dv by dx, and in this case, because I've got this force in terms of x, I'm going to use v dv dx. I can see that I've got m on both sides of the equation, so I can divide both sides by m, and now I can separate and integrate. So if I rewrite the left hand side, I've got this constant gr squared. I'm integrating x to the power of negative 2 with respect to x, and then on the right hand side I would integrate v with respect to v. Now the values of x and the values of v to put in, well, I know that when the distance is 3r, then the velocity is v, and I know that when the distance is r, then the velocity is what I'm looking for, so I'll call that, need to use a new letter, nothing too confusing, let's call this u. Okay, so I can now integrate. So on the left hand side I'll get negative g r squared, and add 1 to the power, divide by new power, and I need to evaluate that from 3r to r. And on the right hand side I get v squared over 2 to be evaluated from v to u, and it's u that I'm looking for. So here I get negative gr squared, and here I have negative 1 over r minus negative 1 over 3r, and here I get a half, which I can take out, u squared minus v squared. So now I can simplify this. So here I have negative 1 over r, basically plus 1 over 3r. So if I multiply the top and bottom of this one by 3, then they have the same denominator. So I have this will cancel with these r's, and so I basically get 1/3 subtract, that was 3 times 1 on there, so I get 1/3 subtract 3/3, which is negative 2/3, but then I get negative negative, so I get 2/3 gr. Then I'm going to multiply it by this 2, and then I get u squared minus v squared, and so I get that u is going to be v squared plus 4 over 3 gr, all square rooted. Okay, so now I found the speed of s as it hits the surface of the Earth in terms of g, r and v. So that part of the question is worth 7 marks. I hope you found this solution helpful. Good luck with your studies.